So, good evening, everyone, and welcome to this lecture. We are done with ray optics, and now we will start with the wave one. Now, you might have heard about the dual nature of light. Have you heard about dual nature of light? Yes or no? Have you heard about light? Light
Yes,
has
sir.
got dual nature. What do you mean by dual nature of light? Anyone? This is just for your academic purpose, and it may not come as a question. Dual nature of anything. Whenever we see things around us, we can consider them in physics. Either they are particles or they are waves. When I talk about particles, particles are discrete. This is one particle, this is another particle. They are discrete, they are not continuous. Whenever we talk about anything in physics, either it's a particle, it behaves as a particle, tuck, 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 tuck. Electron is a particle, proton is a particle. These are particles. Either it's a particle or second, it is a wave. Now, difference between a particle and a wave is particle is discrete. 1, 2, 3, 4, 5, 6, 7, 8. These are particles. But a wave is continuous. Do you understand the difference? Particles are not continuous. They are there, then they are not there. They are not there. So particles are not continuous. They are discrete, but the wave is continuous. We understand this? Light has got a dual nature. What do you mean by dual nature? That sometimes it can behave as a particle and sometimes it can behave as a wave. Now, what we saw in the chapter that we have just done, we have seen two phenomena of light. What were the two phenomena of light that we saw?
Reflection and refraction.
Reflection and refraction. Now, these two phenomena of light, which is reflection and refraction, they can be understood or explained by any one theory. They can be understood if we take light as a particle. They can also be understood if we take light as a wave. So these phenomena can be explained both by the particle nature as well as the wave nature of light. Do we understand this?
Yes, sir.
But there are certain phenomena of light which we see that cannot be explained by particle nature of light. So in this chapter of wave optics, we are going to understand those phenomena of light which cannot be understood by its particle nature, which has to be understood by its which nature?
Dual nature.
By its wave nature. Light has got dual nature. Sometimes it behaves as particle, sometimes it behaves as wave. Right now, we are concentrating on those phenomena which can only be understood by its wave nature. And those phenomena are, can anyone tell me what those phenomena are? Those phenomena are interference, diffraction, polarization. Do we understand this? So these are the three phenomena which we have to understand. Out of this, the first one that we are going to understand is known as interference. Interference is the phenomena that we are going to understand. But before understanding the interference phenomena, let us try to understand the meaning of certain terms. Remember, these terms are going to come, and the most important part of this chapter is to understand those terms that are going to come. And what are the terms that are going to come? The first term that is going to come as soon as we talk about the wave nature of light is known as a wave front. So that is the first heading that we are going to write, wave front. What do you mean by wave front? Anyone? Wave front. Anyone? As soon as we talk about waves, we talk about wavefronts. What do you understand by wavefronts? Have you heard the term wavefront before? Okay, you might not have heard about the term wavefront. This phenomenon of wavefront suggested by Huygens, and this is known as Huygens wave theory. This phenomena was suggested by Huygens, and this is known as the Huygens wave theory. He said that light travels in the form of waves, and one source of light creates these things which are known as wavefronts. What are these wavefronts? When light is propagating in a medium, let us say, the locus of all those points which are vibrating, when light moves, the particles oscillate or vibrate. The locus of all those points which are oscillating in the same phase are known as wavefronts. So what is a wavefront? A wavefront is a locus of all points that are in the same phase. Wavefront is a locus of all points that are in the same phase. When I talk about phase, what do you understand by the term phase? Anyone has any idea about the term phase?
Speed.
No, phase is not speed. Think about something else. Phase means it tells us, and phase is a word that comes from the wave equation. We will understand this term phase in much detail. Just we are going to.
Interval.
Phase is sort of not an interval. Phase means they are doing the same thing. The particles, if they are moving up and down, they will reach their maximum, they will reach their minimum, maximum, minimum, all are doing this maximum, minimum at the same time. We call those particles in phase. Or you can say this in a different way. If two people are running, if they are running together, they are running in phase. If someone is ahead, we call them he is leading. If someone is back, we call it he is lagging. If they are running together, they are running in phase. That is the simplest way that you can understand phase. We will understand phase more nicely once we are done through this definition. Now we are trying to understand wavefront. Wavefront was suggested by Huygens, locus of all points that are in the same phase. Remember some important things about this wavefront. This wavefront is the locus of all points that are in the same phase. The second point is the direction of propagation of wave. The direction of propagation of wave. The direction of propagation of wave is perpendicular to your wavefront. The direction of propagation of this wave, whatever wave is creating this wavefront, the direction of that wave is perpendicular to this wavefront. So for example, if I have wavefront like this, oh, I'm not able to draw a straight line. Let me try it again with this one. If this is my wavefront, if this is my wavefront, which is known as a plane wavefront because it is plane, what might be the direction of propagation of wave? In which direction the wave might be propagating? Can you tell me? Wavefront is like this plane. What can be the direction of propagation of wave? Yes? It might be like this because this is perpendicular. It might be going in this direction like this, or it might be going in the opposite direction. Remember, the wave is the direction of propagation. When I say propagation, that means the direction in which the wave is traveling. The direction of movement or direction of propagation of wave is always perpendicular to the wavefront. Do we understand this? Yes or no? If I have this type of wavefront, and this we will know them by name. This is not the type that I was supposed to draw. This was the type that I was supposed to draw. These type of wavefronts are known as spherical wavefronts. Spherical wavefronts. If my wavefronts are spherical in shape, what would be the direction of propagation of wave? The direction of propagation of wave will be perpendicular to this. Do we understand this? So the wave might be moving like this if the wavefront is like this. Is it getting clear to everyone? What is a wavefront and what is the relation between the wavefront and the direction of propagation of wave? Yes or no? I'll give you 2 minutes to note this down. Have you drawn this, beta?
Sure.
Okay. Now looking at the diagram, you actually saw 2 different types of wavefronts. Actually, there are 3 different types of wavefronts that are possible. And I'm going to show you those 3 types of wavefronts. 2 of them I've already shown. There's also a third type, and it comes on your screen now. So there are 3 types of wavefront that can be there. This is the first type of wavefront. This is the second type of wavefront. And this is the third type of wavefront. What is the first type of wavefront known as? The first type of wavefront is known as
Point source.
the first type of wavefront is known as spherical wavefront. Spherical wavefront, which is produced by a source, which is a point source. Do we understand this? Point source. If I have a point source of light, a point of light, it will emit light in all directions. That point source of light will create a spherical wavefront. Do we understand this? Yes or no?
Yes, sir.
Point source of light creates spherical wavefront. Now, if you would have, I think you have done electrostatics somehow, right? You have read electrostatics, yes or no? Yes or no?
Yes, sir. Up to electric field.
Up till electric field. Now imagine this is not a point source of light, but this is the electric charge. This electric charge will create electric field. The electric field will go in the outward direction. Yes or no? So you can
Yes, sir.
think of it in this way. These are your electric field lines. These are your electric field lines, and this surface is known as equipotential surface. Have you heard about equipotential surface? Have you heard about equipotential surface, my dear friends? An
Gaussian surface.
equipotential surface is always perpendicular to electric field. Have you read that anywhere? This is electric field lines. So a wavefront can be thought of as an equipotential surface for an electric field. The direction of propagation of wave can be thought of as electric field lines. And sorry that you have not done this, but if you would have done this, you could have made the correlation between an equipotential surface and electric field. If you take the direction of propagation of wave as your electric field, your wavefront becomes your equipotential surface. Equipotential means same potential. Wavefront means same phase, same potential. They basically mean the same thing. Do we understand this? The second
Yes, sir.
type of wavefront that we come across is known as cylindrical wavefront, and I can see a cylindrical wavefront right in the classroom that you're sitting at. Your back there is a tube light that is lit, and if you look, tube light is cylindrical in shape. It's the line source of light. A tube light creates cylindrical wavefronts. Do we understand this? That is known as a line source of light. This is same as a line source of charge, a line charge. A line charge creates cylindrical equipotential surface. Do we understand this? So a line source of light will create, this is the line source, just like the tube light that I see, and it is creating cylindrical wavefronts. So that are known as cylindrical wavefronts. Then we have the third type of wavefronts, which are known as plane wavefronts. If we go very far away from any line source, when light was coming from infinity, we were seeing parallel rays, yes or no? Do we remember when light was coming from infinity, we were seeing parallel rays? Do we remember those rays which were coming from infinity?
Sir.
These are the rays that were coming from infinity. And if I draw surfaces perpendicular to this light rays, they become my plane wavefront, the same wavefront that I had drawn to you for you. So when you are very far away from any line source, any light source, whether it's a point source or it's a line source or any source, you will see that rays are coming parallel. So your equipotential surface or your wavefront becomes plane. Do we understand this? Do we understand this? That are the three types of wavefronts that we encounter. You understand this? You understand
Yes,
it?
sir.
Then there is something known as the Huygens principle. We will quickly go through this Huygens principle. What does this Huygens principle say? Whenever we have a source of light, it will emit wavefronts in all possible directions. So light will move in the form of wavefront. Light travels or propagates in the form of wavefronts. Now, how did he explain how do these wavefront move forward? So he said that every point on the wavefront, if I have a wavefront, and let me take a picture of a wavefront to suggest what I'm going to say next. So every source of light is going to create a wavefront. Then what is going to happen is this. Let me show it to you what is going to happen. Okay. So here is this. This is just for your academic purpose. No one is going to ask you this Huygens principle. This is a wavefront that the light source has created. Now, what Huygens suggested that every point of this wavefront, this is one point, point number one, this is point number two, second point of the wavefront, this is point number three, third point of the wavefront, this is point number four, fourth point of the wavefront, and fifth. Every point of this wavefront becomes a new source of light. He says that every point becomes a new source of light which emits its own wavefronts, You can see this is the wavefront. This is the wavefront emitted by the first light source. This is the wavefront by the second light source. This is the wavefront of the third light source. This is the wavefront of the fourth light source. And this is the wavefront of the fifth light source. So every point on a wavefront, and remember this is just for your academic purpose, any point on the wavefront becomes a source of light and it emits its own wavefront, its own WF. WF means wavefront. These wavefronts are known as secondary. These wavefronts are known as secondary wavelets. You can see secondary wavelets. These wavefronts are known as secondary wavelets. A surface touching all these secondary wavelets in the forward direction gives the position of next wavefront. This next wavefront is known as your secondary wavefront. So what do you see, my dear friend? Here is we have one wavefront, which is your primary wavefront. On this primary wavefront, there are infinite number of points. Every point becomes a source. That source emits its own wavefronts. And if I draw a surface which touches all these points, all these secondary wavelets, that gives us the position of the next wavefront. This next wavefront is known as the secondary wavefront, and this is how light will propagate. Now, this secondary wavefront will now become the primary wavefront. Every point on this wavefront will become a source. They will emit their own secondary wavelets. And if you draw another surface touching all these secondary wavelets, that will give you the third wavefront. Then that third wavefront becomes your first wavefront. Do we understand this? This is how light propagates. Light propagates in the form of wavefronts, and this principle is known as Huygens principle. Do we understand this? It's a part of your academics, just for your board exams. This is not going to affect anything in your JEE. You will hardly get question in JEE based on this. The only question they can ask is from this part: what type of wavefronts can this type of body create, and what is the definition of a wavefront? That is all that we need to know: the shape of wavefronts and who creates what type of wavefronts. And if you know wavefront, can you tell the direction of the light wave? Do we understand this? Yes or no?
Yes, sir.
That is all that we need to know in this particular thing of wavefront. I'll give you a minute to note this down. Have you noted this down?
No, sir.
Please note it down, beta. Give you a minute to note it down, then we will move ahead.
Sir, can you please next slide?
Yes, beta?
Sir, can you please show the next slide?
Okay. The slide is, I think I've changed the slide. Okay, I'll just get that slide of Huygens principle. Remember, this Huygens principle is just for your theoretical knowledge, nothing else. Don't expect a question from here.
Done, sir.
Okay. Yes, beta, any problem? Have you done this?
Still writing, sir.
Okay, I'll give you 2 minutes. Don't worry. Shall we go ahead?
Yes, sir.
Okay, chalo. Now, as soon as we have understood the term wavefront, here in this chapter, we are going to deal with waves, and therefore we'll have to deal with the equation of a wave. Now, the equation of the wave, what we are going to deal here, well, the actual equation of wave, the equation of a progressive wave, it consists of all the particles at all the times. Right now, what we are going to consider here are sinusoidal waves of just 1 point or 1 particle. Now, how do we write the equation of a sinusoidal wave? So let us try to understand the equation of a sinusoidal wave. When I say sinusoidal, so that means that it is in the form of either a sine wave or a cos wave. Let us take the example of two of such waves, or let us start with one wave only. Okay, so let me write the equation of the wave in this pattern. Y is equal to a sine omega t plus phi. Y is equal to a sine omega t plus phi. Now, what are the meaning of the different terms that are appearing in this equation? What does y stand for here? Anyone? What does y stand for here? No one knows it? No idea what is y?
Sir, it is the displacement of the wave.
Displacement of, we are not talking about wave, the complete wave as such. We are talking about the displacement of a particle on the wave, right? So this is a displacement of the particle. Do we understand this? Displacement of the particle of any particular particle we are talking about. T, what does T stand for? T is definitely time. Yes or no? At what time, where is your particle? What does A stand for?
Amplitude.
A stands for
Amplitude.
amplitude. What do you mean by amplitude? It is the maximum displacement of particle from its mean position. Do we know this?
Yes, sir.
Please note it down. This is the maximum displacement of particle from its mean position. What matters in this particular topic is that you understand these terms. What is omega here? Sine is the sine wave. So sine is that trigonometric term sine. What is omega here?
Angular momentum.
Angular?
Momentum.
Angular what? I could not hear you. Can you speak a bit louder, beta?
Angular momentum, sir.
Angular momentum.
Angular velocity.
Yes, it is angular velocity. Instead of calling it angular velocity, we are talking about a wave. So to understand in terms of angular velocity may not be correct. Better we call it as angular frequency. Do we understand the meaning of the term angular frequency?
Yes, sir.
Angular frequency. Okay. Now, since we have talked about angular frequency, let us talk about T. T is known as time period. Do we know this time period for a wave or for a particle in a simple harmonic motion? T, time period, is the time taken to complete one. Time taken to complete what? Complete one revolution or one oscillation. Do we understand this T, time period? The SI unit is seconds, yes or no? Do we understand time period, capital T?
Yes, sir.
Okay. If I inverse this, if I reverse this, it becomes F. F is 1 by T. It is the number of revolutions in 1 second. We all understand this? Number of revolutions in 1 second. Its SI unit is hertz. You have heard about this unit hertz, HZ, hertz, 1 by second? Yes or no?
Yes, sir.
Now, as soon as we understand what is frequency, then we can understand what is angular frequency, and we can understand the relation between the three quantities. Omega is known as angular frequency. It is 2 pi f, or you can write it as 2 pi by t. It is the angle turned in 1 second. Is the concept of angular velocity omega clear to everyone? Yes or no?
Clear, sir.
Okay. You must be clear with each and every terms, because if you get confused with the terms, the entire exercise goes in vain. Can anyone tell me what is this phi? Yes, beta. This phi is an angle. What is this actually known as? Idea? No idea. This is. I'm sorry, I did not hear you, beta. This is known as initial phase, or sometimes we call it by the term EPO, EPOCH. Initial phase or EPO. This entire term which is there inside this bracket, this entire term which is there inside the bracket, the yellow term, all the terms together, they are basically sign of something, right? Sign of something. Sign of something, you can only find sign of an angle. So this entire thing in yellow is basically an angle. Do we understand this?
Yes, sir.
The entire term in yellow is basically an angle. This entire thing completely is known as the phase of the particle. This entire thing completely is known as the phase of the particle. Now you can understand what do you mean by the phase of the particle. The phase of the particle basically tells us where the particle is. If we know the phase in terms of angle, we can tell, okay, the particle is here. Okay, now the particle is there. Okay, now the particle is here. This entire term is known as phase. And phi is known as initial phase. So basically, when I put time at 0, if I put time at 0 in the equation of phase, it is omega t plus phi. If I put t as 0, it becomes phi. Therefore, phi is known as initial phase. Do we understand this? Yes or no?
Yes, sir.
These are the meaning of these terms that first here for us, A standing for amplitude, maximum displacement, Y is the displacement, T is time, omega is angular frequency, phi is the initial phase, omega t plus phi is known as the phase. Have you noted this down, everyone? I'll give you a minute to note it down. Do it fast.
Done, sir.
Everyone has done this?
Excuse me, sir.
Yes, beta.
Sir, can you please tell what is the heading?
Can you please tell what is the
Equations heading.
what is the
Heading of the equation, sir.
equation of a sinusoidal wave? Sinusoidal means sine wave. Equation of a sinusoidal wave, sine wave, nothing else. Okay?
Oh, yes,
Is
sir.
it visible to everyone now?
Yes, sir.
Okay, I'll give you 1 minute to note this down.
Completed, sir.
Okay, completed, sir. Everyone has completed this?
Yes, sir.
Now, we have seen what is a wavefront. A wavefront is a locus of all points which are in the same phase. Now, let us try to understand what do you mean by same phase. Let us suppose that I have two waves or two particles. One is y is equal to a 1 sine omega t plus phi 1. Oh, let us not put it as phi 1. Let us make it simple. One of the wave is given by this. Y1 is a1 sine omega t, and the second wave is given by y2 is equal to sine omega t plus phi. Okay, now something have been kept same knowingly and something have been made different knowingly in the two equations. Y1 is the equation of the first wave, y2 is the equation of second wave. Now, can you tell me what all things are kept same and what all things are made different in the two equation? Look at the two equation. What things you find similar in both the equation and what things do you find different in both the equations? Yes. What all quantities are similar, same in the two equations and what quantities are different in the two equations? Yes.
Angular frequency and time.
Time, okay, time is a variable quantity. I cannot keep it same. So basically what I have kept same is omega. T is, they are a function of t. So t is going to keep on change, will keep on changing. Y is given as a function of t. So omega is kept same. So they have the same angular frequency, or I can say they have the same frequency, or I can say they have the same time period. So omega is kept same. Some things have been changed. If you look at these two, the amplitudes are different. The first wave has an amplitude of A1. The second wave has an amplitude of A2. A1 and A2 are different, amplitudes are different. One more thing is different. What is the other thing that is different? What is the other thing that is different? If I look at this term here, omega t, is known as the phase of wave 1. Yes or no? This is the phase of wave number 1. If I look at this entire term, this is the phase of wave number 2. Do we understand this? These two waves are not in the same phase. These two waves are not in the same phase. They have a phase difference between them. That is what I mean when I say in the same phase or in different phases. If this angle, what is there with sine? If the angle is same, they are in the same phase. If that angle is different, they are in different phases. So wave number 1 and wave number 2 are not in same phase. Do we understand this? Y1 and Y2 are not in same phase. Do we understand this? Yes or no?
Yes, sir.
If y1 and y2 are not in same phase, they have a phase difference. What is the phase difference? So delta phi means the difference in phase. Phase of wave 2 phi 2 minus phase of wave 1 phi 1. So I will call this as the phase of wave 2 phi 2, and I will call this as phase of wave 1 phi 1. So I will subtract phi 2 and phi 1, or phi 1 plus phi 2, I get the difference in phase. And if I subtract it here, I will get omega t plus phi minus omega t. So I will get it as phi. This is known as the phase difference between the two waves. Do we understand this? Yes or no?
Yes, sir.
Now, when two waves are not in the same phase means running together. Different phases mean someone is ahead and someone is behind. Now, if they are not in the same phase, someone is ahead, leading, someone is piche, lagging. Who is ahead and who is behind? Which wave is ahead? Which wave is behind? You have the two waves in front of you. They are not in the same phase. Someone is leading, someone is lagging. Who is leading? Who is lagging? Yes, my dear friends. Who is leading? Who is lagging? Y2.
Y2 is leading.
Well done. Y2 is leading
Is like
Y1 by a phase angle of phi. Do we understand this? This is one way you can say this, or the other way of saying the same thing is, what is the other way of saying the same thing? Here I have said, my dear friends, that y2 is leading y1 by phi. I can say this in a different way. How can I say this in a different way? Y1 is lagging y2 by a phase angle of phi. Do we understand this?
Yes, sir.
So this is what we mean by the term phase difference, leading and lagging. I'll give you 2 minutes to go through this.
Completed, sir.
What about the other class?
yes, sir.
Anyone has noted this down?
Yes, sir.
Okay. That means we can move ahead. Now we have talked about the most important thing of this chapter is only this what we are discussing right now. We have talked about phase difference. Then there are two more terms that might come. So write the next heading, phase difference, not phase difference, path difference, and time difference. Three types of differences or three types of things will come: phase difference, path difference, and time difference. Phase difference is denoted by delta phi. You've just now seen it. Path difference is denoted by delta x. And time difference is denoted by delta t. Delta stands for difference or change. Phi stands for phase. T stands for time. And x stands for path. Do we understand this? Now,
Sir.
there are 2 or 3 more terms that we have to see in wave, and which we see now. If I draw a wave, and I'm going to try it now. Oh, let me just make it like this. Okay. If I try to make a wave, I will make the wave like this. A sine wave. Do you know a sine wave? A sine wave looks like this. Yes or no? Anyone knows a sine wave? Yes or no? This, let us say, is time, and I have plotted the displacement y like this. This is a sine wave, right? This is the maximum displacement. We call this maximum displacement as A. Do we understand this maximum displacement as A? Yes or no? Is it a yes? Is it a no?
Yes,
Huh?
sir.
If I talk about time, here the time is 0, and here it will be equal to capital T. Capital T stands for the time period. This is the time taken to complete one oscillation. This is one complete oscillation of the wave. Do we understand this? Yes or no?
Sir.
0 to T. If I take the middle point, this is T by 2. Yes or no? This is T by 4. And this point will be 3T by 4. We all understand this, or it is going above our head saying bye-bye? I'm going above our heads. Bye-bye. Bye-bye or not bye-bye? Yes or no? Okay. I'll do the same thing in terms of wavelength. Here the wavelength is, here the wave is starting. Wavelength, in terms of wavelength, it is 0. Here the wavelength is lambda. Do you understand wavelength? Wavelength of a wave, yes or no?
Yes, sir.
The wavelength is lambda. At this point, the distance between this point and this point will be lambda by 2, yes or no? This will be lambda by 4. This will be 3 lambda by 4. So the same thing I have marked in green for wavelengths. In red, I have marked it for time period, in terms of time period. In the green, I have marked it by wavelength. Do we understand this? Yes or no? This is the equation of y is equal to A sine omega t. Do we understand the red and the blue marking that I have done? Yes or no?
Yes, sir.
The same thing I can mark in terms of angle. How much angle will it turn? So if I mark it in terms of angle, and let me call the angle as 0 here, the angle here would be 2 pi, because one complete oscillation means an angle of 2 pi. Yes or no?
Yes, sir.
So here the angle would be pi. Yes or no? Here the angle would be pi by 2, and here the angle would be 3 pi by 2. So the same thing, I have marked all the points in terms of time, in terms of lambda, and in terms of the angle. Yes or no?
Yes, sir.
Okay. This T is known as time. Lambda is the wavelength, and 2 pi or pi by 2 is the angle. Now we can see, and that we'll discuss in the next class, between this point, pink point, and this point, the angle changes by 2 pi. Yes or no?
Yes, sir.
But time changes by t, and path or length changes by lambda. From here, we can derive a relation between phase difference, path difference, and time difference. What is the relation? A phase difference of 2 pi is equal to a path difference of lambda, which is equal to a time difference of capital T. Do you understand what I have written?
Yes, sir.
If 2 points in terms of phase, they are having a difference of 2 pi. In terms of time, they will have a difference of T, time period. And in terms of wavelength or length or path, they will have a difference of lambda. From here, I can find out a relation between path difference, phase difference, and time difference. We'll do that in the next class. I hope you have understood what we have done in the previous class. I mean, in this class. In the next class, when you come, please go through what we have done in this class, else the next class becomes very difficult to understand. So I'll see you in the next class. Take care. Have a nice day. Anything else you want to ask? You can go ahead and ask.